All right, in Calculus, Chapter 1, Section 2, we'll be finding the limits today graphically and numerically. I'll talk a little bit about how we'll be doing them in the rest of the chapter, like where we factor and reduce and things like that, just to kind of get us ready for the next couple days worth of notes. Our objectives today are going to be use a limit using numerical and graphing approach, different ways that a limit can fail to exist, and study and use a formal definition of a limit. So suppose you're asked to sketch the graph of this function f given by this function. F of x equals x to the third minus 1 over the quantity of x minus 1, provided x does not equal 1. The reason why x can't be 1 is because remember we can never divide by 0. If I was to plug 1 into this denominator, I would have 0 there. So it's telling me that for all values other than x equal 1, you can use a standard curve sketching techniques. So in other words, if we know how to graph our functions, sometimes then we'll be able to answer the limit questions about them just from understanding the graphing point of view. So if I was to take a look at a table of values as x gets close to 1, notice we started out at 3/4, then 9/10, then 99 hundredths, 999 thousandths. These values are getting closer and closer to 1 for the x. Notice from the right side they're larger than 1, and again they're getting closer and closer to 1 as well. If you were to plug those into your calculator into y equals for this function right here, and look at the table, these would be your y values from the table. What are these y values getting really close to? See, that's what we're looking for. See, as x gets close to 1, what are the y values getting close to? And hopefully you're looking at that and going, well, those y values right there are getting close to 3, and that would be correct. And again, like I said, in Lesson 1, it's about the graph or it's about the table, but I'm going to go ahead and show you how we'll be doing this in the rest of the chapter. And so again, on my test, I'm not going to have you fill in a table on my test. You're not going to use a graphing calculator. So therefore, you will only have to fill in the table ones in your homework. So if we did this algebraically instead of the table format, I do notice that this numerator is a difference of cubes. So we would factor our difference of cubes. So that would give me the x minus 1 for the first factor. The second factor was the x squared. You multiply the two, change that sign, so that's the plus x, and the last one squared is plus 1. I want you to notice the x minus 1s would reduce. Leaves you with x squared plus x plus 1. But realize that these had reduced. When a function has two binomials that reduce, that does give you a hole in your graph. Where is the hole? Well, you take that value that reduced, x equals 1, and you plug it into what's left over. So 1 squared plus 1 would give me 3. So I have a hole in my graph at 1, 3. See, the graph of this original function is that parabola, but with a hole at the point 1, 3. This is what the picture would look like. So if I was to ask you, what is the limit as x approaches 1, that means what is y getting really close to when x gets really close to 1? See, as the x here got very, very close to 1, this y value is getting very, very, very close to 3. That's what this is showing you right here with an open circle in that graph. So writing it with limit notation, that would be the limit as x approaches 1 of the function equals 3. Again, that means what is the y value is getting close to when the x is getting close to 1? Now y's were getting close to 3. So this time we're going to evaluate a different function as x approaches 0 of this one right here. Now if I plug 0 into the numerator, I get 0. I plug 0 into the denominator, I have the square root of 1, which is 1, minus 1 is also 0. So I get 0 over 0. We can't have that. That's actually called an indeterminate form. So we'd have to do something else with it. Now again, this first lesson was about the tables. So they would actually have you go to y equals in your calculator, you go to the table, and you go ahead and plug in these values. Now when you plug in the values, you're looking for what is the y getting really close to as the x's are getting really close to 0. And hopefully you notice these y values right here are getting close to 2. So if we did this without the table, what we will do is we want to rationalize that denominator. We want to get rid of the square root in that denominator. We want to multiply by its conjugate. So we're going to multiply by the square root of x plus 1, change this sign, that's why it's the plus 1. Now in the numerator, never FOIL it out, never distribute it out. Just leave it factored. The denominator, though, if you were to have done the FOIL, so the first terms would be a pair of x plus 1s right there. Remember, the outer and the inner would have canceled. That would give me 1 radical x plus 1 minus 1 radical x plus 1. So that's gone. The last terms, multiplying those two, would give me the negative 1 down here. Now in that denominator, I noticed the 1 minus 1 would go away. That would give me just an x on the bottom. Notice this x reduces. If things don't always conveniently reduce, you did something wrong. So go back and look for your mistake. Now if I plug 0 into what's left over, I have the square root of 1, which happens to be 1, plus 1. That answer would be 2. And a minute ago by the table, we had the answer of 2 as well. So to simplify this one, if I plug in 3 in the numerator right here, this would be 1/4 minus 1/4. That whole thing is 0. 3 into the bottom is also 0. 0 over 0 is not allowed. It's called an indeterminate form. So what if I manipulate this problem and multiply everything by the least common denominator? Because I have fractions within fractions, which we're not allowed to leave. So I would want to multiply everything by the x plus 1 and by the 4. So when I take this red stuff times that first fraction, the x plus 1s are gone and gives me 1 times 4, which is where I got this 4. Then if I take this fraction of 1/4 times the red stuff, the 4s are gone and gives me minus the x plus 1. In the denominator, never FOIL it out, multiply it out. So you remember the numerator I am because I'm trying to get rid of the denominators here, those fractions. In this case, I want to just leave this in factored form because it should conveniently, something should go away so that I don't get a 0 over 0. So in that numerator, if I distribute this negative sign right here, I have 4 minus x minus 1. I'm looking at 3 minus x and x minus 3. They look kind of similar. Hopefully you're noticing that and going, wait a minute, those are opposites. See, when you divide those, you actually get negative 1. So I would get negative 1 over 1. So this becomes negative 1. That becomes 1. Now if I plug in the 3 into this, 3 plus 1 is 4. So my answer would be negative 1/16. So show that this limit does not exist. First off, if I have the graph of absolute value of x over x, I want to look at a table. I don't know what this graph looks like. So absolute value of x over x. I would start with x can never be 0. So 0, I already know. This does not exist. So I want to plug in numbers to the left of 0 and numbers to the right of 0. Whatever the break in my graph is, go ahead and put that in the middle of your table and then plug in points around it. So if I was to plug in, say, negative 3, the absolute value of that would be 3 divided by negative 3. That'd be negative 1. The absolute value of negative 2 is 2 divided by negative 2 would be negative 1. Absolute value of negative 1 is 1, but divided by negative 1 is negative 1. Notice these will all be negative 1. Now the 0 didn't exist. That was undefined. Plugging in 1. The absolute value of 1 is 1 divided by 1. Absolute value of 2 is 2 divided by 2. Absolute value of 3 is 3 divided by 3. And this is what your graph looks like. Now, these are both open circles in case you can't tell on your copy. So what happens here, if I ask you for the limit as x approaches 0, see, is the y value approaching a single number from the right and from the left? Hopefully you're thinking, no, it's not. See, from the left side, this y value is approaching negative 1. From the right side, the y value is approaching 1. Again, this is looking at x equals 0. So if I'm looking at x equals 0, which is right here, then from the left side, that y value is negative 1. From the right side, the y value is positive 1. Therefore, then that limit doesn't exist. It has to be the same from both the right and the left for the limit to exist. Now, if I was to make this graph, instead, this graph would be shifted to the right 3 units. So you do need to remember your shifting of graphs right, left, up, and down. Remember, on the inside with the x is the backwards, right and left. And if I had done a plus 3 at the end of this, then it would shift the whole graph up 3. And this will end our part 1 for our first lesson here.